Hello students, in this video we'll see how to solve differential equation when there's a substitution that's suggested by the equation itself. So let's consider the ODE. Y prime equals 1 plus 6x e to the x minus y. This equation is not exact, it's not linear, it's not separable, so we need to examine the equation more carefully to figure out how we can approach it. What we can do is we can notice the x minus y in the exponential. The problem would be simpler if there was just a single term in the exponential. So what we can do is we can substitute. We can let u be x minus y. Now we have to recall that in this problem, y is the dependent variable and x is the independent variable, which tells me that du dx, or u prime, will be 1 minus y prime. And this will tell me, therefore, that y prime, if I put the y prime over on the other side of the equation, is 1 minus u prime. Now we can substitute into our original equation. Our original equation will now become 1 minus u prime, which is my y prime, is equal to 1 plus 6x, the x remains the same, e to the u. Now there's a 1 on both sides of the equation, so the 1 will cancel out. So I will have negative u prime is equal to 6x e to the u. Now we will write this in differential form as negative du dx is equal to 6x e to the u. And I will separate the equation, writing this as negative e to the negative u du is equal to 6x dx. And now we solve by integrating. So the integral of negative e to the negative u du is equal to the integral of 6x dx. And so this will give me the solution to my differential equation. So the antiderivative of e to the negative u with a negative sign is just e to the negative u will be equal to, an antiderivative of 6x squared is 3x squared plus c. And then I finally substitute. We know that u is x minus y, so my solution to my differential equation is e to the negative x minus y is equal to 3x squared plus c. And so there is the solution of our differential equation by substitution. So let's see another example of this. Let's consider this differential equation. Let's solve 2x plus y plus 1 dx plus 3 2x plus y dy equals 0. And so rather than solving the entire equation, let's make the following observation. Let's note that I see a 2x plus y over here and a 2x plus y over here. So if we let u be 2x plus y, this will imply that du is 2 dx plus dy. And now we can substitute in and figure out what the variables are going to give us. So what will happen over here is my differential equation will now become a u plus 1 dx plus 3u, and now I'll have a dy. But we see from the above equation that dy is really du minus 2 dx. And this is equal to 0. And so now we can rearrange our terms. Our terms will be, let's collect the dx terms. I will have a negative 6u dx and a u dx, so that will become a negative 5u plus 1. and those will be the dx terms, plus the du terms are going to be a 3u du equals 0. And now this equation is separable. So I will divide by 1 minus 5u, so I'll have a dx plus 3u over 1 minus 5u du is equal to 0. Now the resulting equation after the substitution is a separable differential equation. And so now the solution can be found simply by integrating both sides of the equation. But in both of the previous examples, we see that by examining the equation and making an appropriate substitution, the problem can turn from a problem which is not separable into a problem which is separable. And this technique is fairly common in ordinary differential equations. When you look at an equation and it doesn't fit the bill of one of the equations you know how to solve, you should try to make a substitution or look for a differential which allows you to solve the problem. Thank you very much.